What we want to talk about today is how you can use the geometry of the coordinate plane to keep track of where you are. Well, the standard approach is to take the coordinate plane in terms of two given coordinates represented by x and y axes. The x-axis is by default the vertical, or by the horizontal one. It goes across left to right, and the y-axis is the vertical one. It goes up, so that the two that intersect, these are like number lines, and the places where the number lines values are each 0 is the place where the coordinate axes intersect. That is called the origin of the plane. And the x-axis and the y-axis split the plane up into four regions. The four regions, since there's four of them, are called quadrants. Quadrant 1 is, by convention, the one where there is a positive direction out. If this is the number line, these are the positive x values. If this is a number line, they're the positive y values. So positive x and positive y puts you in this area. That's called quadrant 1. If you go a negative x and a positive y, that puts you in this area of the plane. That's quadrant 2. Here's quadrant 3, negative x and negative y, and then quadrant 4 would be positive x and negative y. So you're working your way around the plane counterclockwise. By convention, this is just the way it's evolved that people enumerate these: 1, 2, 3, quadrant 4. And you can keep track of what those quadrants are by the inequalities that the coordinates satisfy. Let's use that to apply this to a fact about triangles. This is a trigonometry course, and it's supposed to be about triangles. So let's make a triangle from the fact as given that there's a point in the plane and another point in the plane, so a pair of coordinates and a pair of coordinates, and how far it is from one to the other is the distance, d. Question is, how is d related to these numbers, x1, y1, the coordinates of the lower point, and x2, y2, the coordinates of the upper point? Well, let's keep track by looking at the coordinates as giving two different types of information about direction. There is a vertical part and a horizontal part. Vertically, we're going from x2, y2 straight down. If you go straight down, you're going to be perpendicular to the x-axis, parallel to the y-axis it would hit. And then we could go horizontally from x1, y1 across. Parallel to the x-axis, parallel to the y-axis gives an intersection, an angle here that matches this angle. You lay out the coordinate axes so that that is a right angle. So this is a right angle. Let's make it a right angle. And now let's keep track in this triangle what the lengths of the sides are. D is what I'd like to know. This vertical side is how far you're going from this point up. Well, what are the coordinates of this point? This point has an x-coordinate and a y-coordinate. The x-coordinate is the same. You go as far over to get to this point as you go to get to this point. So the horizontal distance across matches. That's the x-coordinate. So this point has x-coordinate that matches this, x2. And it has y-coordinate, how far up you go, matches how far up you go to get to this point. So the y-coordinate is y1. This point has coordinates x2, y1, and now we can keep track of what the length of this side of the right triangle is. It's from a point that is y1 units up to a point that's y2 units up. So how far up you go from y1 to y2 is the length of this side. That is y2 minus y1. In the same kind of reasoning, horizontally you're going from x1 to x2, so this is x2 minus x1. Now you know the Pythagorean theorem. If you've got a right triangle, one side, another side, and the hypotenuse, the sum of the squares of the two sides matches the square of the hypotenuse. That's what the Pythagorean theorem says. Here it says, with the sides labeled the way we've done, it says x1 minus x2 minus x1 squared, that's the horizontal side, y2 minus y1 squared, that's the vertical side, matches d squared, that's the hypotenuse. Now, we'd like to just know what d is, so we can get that by taking the square root on both sides of the equation, the square root of that sum. You can't write it any simpler than that way. So the distance is in terms of the x-coordinates of the 2 points of that bound the line segment, and the y-coordinates of the points that bound the line segment gives this combination matching the distance from one point to the other point. This is called the distance formula, and we'll use that lots of times to come up with a numerical value for how far it is from one point whose coordinates are given to another point whose coordinates are given. Let's try using it for just a sample problem. Pick 2 points kind of at random, 3, 8, so the x, y coordinates of one point are given, the x, y coordinates of another point are given. Let's find the distance between those points. We've got x1 is 3, y1 is 8, x2 is minus 1, y2 is 2, and I'd like to use this in that distance formula that we derived. So d for the distance from P1 to P2, difference in x coordinates squared, difference in y coordinates squared. Let's plug the numbers in. x2 is minus 1, x1 is 3, so minus 1 minus 3. y2 minus y1 is 2 minus 8. Let's do the arithmetic. Minus 1 minus 3 is minus 4. 2 minus 8 is minus 6. So under the radical, we've got minus 4 squared and minus 6 squared. Minus 4 squared is 16. Minus 6 squared, minus times minus is positive, so it's 36. 16 plus 36 happens to add up to 52. If you play cards, you know there are 52 cards in a deck. That's 4 suits of 13 cards each. So 52 is 4 times 13, and the square root of 52 is the square root of 4 times 13. Square root of 4 is 2. Square root of 13 is whatever it wants to be. It sits there. You can't simplify it anymore. But you can write the distance from one given point to the other given point as this real number, 2 times the square root of 13. And that would be the right way to write it. Now let's try graphing a problem. Let's try graphing a function. Y is minus 3x plus 5. This is a special form of a function. It's an equation relating y and x. It gives y as a function of x, since y is exhibited as a rule in terms of x values that you can plug in. One way to understand this equation is to see it algebraically, this relation between the y variable and the x variable as given. Another way to understand it is to see what it does numerically. Try plugging in particular x values and seeing what comes out for the y values that are associated with them. For instance, if x happened to be 0, you could plug 0 in to this side of the equation, and out would come for y minus 3 times 0 plus 5. So the number 5 goes for y goes with 0 for x. Try x is 1. Minus 3 times 1 plus 5 is minus 3 plus 5. That's 2. So when x is 1, y is 2. Picking some other numbers out kind of at random. If x is 5, minus 3 times 5 is minus 15, plus 5 is minus 10. And if x happened to be minus 1, then minus 3 times minus 1, minus times a minus is plus. So plus 3, and then 5 added gives 8. So what we've got is a set of numbers just kind of trying to plug in different numerical values for x to see what comes out for y, and what happens is something you could summarize in a table. So this is a tabular form for the relation between x and y summarized by this equation. So we've got it algebraically, we've got it in a table. Another way to understand the relation between x and y is to do it graphically. And to do that, think about the x and the y as values of the variables plotted on the x-axis and the y-axis. So when x is 0, we could plot the point 0, 5. x 0, y equals 5. x equals 0, y equals 5 is right here. X equals 1, y equals 2. So 1 unit over and 2 units up. Notice to make these points fit, I've got the scale a little different. 2, 4, 6, 8. Y is going up by 2s. X is spread out more, going up by 1. So there's the scale for x and y. And those 4 points have these diamond-shaped things that show up as the points plotted in the coordinate plane. Don't lose this one that's hiding on the axis. And another thing, it looks like I made a little mistake keeping track of this vertical scale up and down to make it fit. I'm going up by 2s. 2, 4, 6, 8. Minus 2, minus 4, minus 6. This should be minus 8 right here, not down low. Minus 8. This point's actually minus 10. And if you go minus 10 for y and 5 for x, 5 units over, minus 10 down, that's that point. 5 for x minus 10 for y is what we've got. So 4 points, and what makes this an example of what's called a linear equation is if you connect the points, they all line up on a straight line, and all the points that are also on that line are also points with coordinates x, y that satisfy that given equation. So lots and lots of points work. Sometimes it's worthwhile to keep track of a feature of a graph. A useful feature is where the graph crosses the coordinate axes. That's good because that kind of anchors the graph to the coordinate axes. So here, looks like it crosses at 5, 2, 4, between 4 and 6, so probably at 5. And over here it crosses probably between 1 and 2, maybe at 1.5 or of some value. So you've got this point and this point as places where it crosses the y-axis, it crosses the x-axis. This is called the x-intercept of this graph. This is the y-intercept. In general, the points at which a graph crosses or touches the coordinate axes, those are the intercepts. You could do it not just for linear equations, but for lots of equations. Let's do it for a fancier one. This blue curve swooping around the plane is just the graph of some, presumably some equation relating x and y coordinates. The way it's lying on the plane, it crosses the x-axis at 1, 2 places, and it touches the x-axis at a 3rd place. Whether it crosses or whether it touches, it counts as an intercept. So this has 3 points that count as x-intercepts. At the same token, here is the place where the graph crosses the y-axis. It only crosses the y-axis once, so this one place is called the y-intercept of the function. So we've got a graph that has 3 places it crosses or touches the x-axis, 1 where it crosses or touches the y-axis, and we end up with that description of what the graph looks like. Good thing to be able to do. And that's the story about distance for today.